All right, we're here to talk about uh, finding force components. Okay, so taking forces and splitting them into components is, and then using that in a sigma f equation is what we're talking about today. So, for example, let's say that I have a problem, and we'll start with something pretty straightforward here. What if I have, here, we'll take this book, and I've got this string attached to it, okay, and maybe I'm pulling it along at a nice constant velocity. Okay, so it's getting pulled along, nice constant velocity from left to right. All right, well then we can do that force diagram pretty swiftly here. Right, we'd say, hey, I've got my sketch, chung 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 chung, right? There's the book, there's a string attached to it, right? And it's being moved at a nice constant velocity to the right. Okay, and so I do my free body diagram. I'd say here I'm doing that side view of the book, and I'd say, okay, what forces are acting on the book? You'd say ranged forces first. You'd say, well, there's a large massive object nearby, that being the Earth, and so there's going to be a gravitational force on the book by the Earth. Right. Next we go to, and you say other range forces, but there's nothing electrically charged here, so there's no electrical force. We're not dealing with particles inside the nucleus of an atom, so we don't have to worry about the nuclear forces. That does it for range forces. Now we go to contact forces. Those are going to be forces between things that are actually touching the system. And so you say, hey, what's touching the book? Just two things, the rope and the tabletop, desktop here we'll call it. And so you say, okay, well, so now we're going to run through our forces. So there's normal and there's friction and tension, our contact forces. But what I do first is list everything touching the system, because that's to be touching. So we said the rope, the string, and the desktop. Let's start with the desktop. So the first question is to see if there's a normal force. You ask, are the surfaces being pressed together? And you say, sure, the Earth is pulling it down against the desktop. So the desktop will push back with a normal force. Once you have a normal force, there's a chance that you'd have a friction force. You have to have a normal before you can have a friction. And so you say, hey, those surfaces, the way you check for friction is, are those surfaces trying to slide past each other? In this case, not only is it trying to slide against the desktop, it actually is sliding along the desktop. So there will be a friction force between them. Friction always goes against the sliding. The book is sliding to the right, so friction will go to the left on the book. This is my friction force on the book by the desktop. Because those surfaces are actually sliding past each other, this is a kinetic friction, by the way. Okay, the other thing touching is the string. Now, strings and ropes and wires and chains and all that, the question is that we ask is, are they being stressed? And you say, yeah, there's definitely, stress on that string, right? Okay, as it pulls along. And so that's a tension force. Tension forces always go along the string and they always pull, they don't push. So it's going to go horizontally along the string. That's their tension force going to the right. Okay, away from the system because it's always pulling. And that's it. There's nothing else touching my system, so I'm done. That's my force diagram. And so now I can go ahead and write my expressions. So what we do here is we'd assign coordinate axes. We're going to be doing, and you say, the first coordinate axis always goes along the direction of the motion. Now we're talking about sliding left-right, so we have a coordinate axis that goes left-right. Okay, it's traditional to call a horizontal axis the x-axis. And then up and down here, okay, the vertical axis would be at a right angle to that. Our coordinate axes are always at right angles to each other, perpendicular to each other, orthogonal to each other. It's traditional called the up and down one y. Now what I need to do is choose directions to call positive, right? And the opposite directions will be negative. It's traditional to call up and right the positive direction, so I indicate that by putting a little plus sign there. If I had something that was sliding left, maybe I might prefer to call left the positive direction and right negative. For now, there's no reason to change it from the standard like this. Okay, so now I'm going to go to my formulas. We know that if I add up the forces on a system that's in equilibrium, those forces should add up to 0. Now I can do that for one coordinate axis at a time. So I might just talk about the horizontal forces, the forces that are acting along parallel to the x-axis. and that those should add up to 0. Or I can talk about adding up all the forces that are going along the vertical axis, the y-axis, up and down, and that those should add up to 0. So now I'm going to use the labels from my force diagram and show how those add up to 0. So for the horizontal direction, I'm going to do forces right minus forces left, because we're calling to the right positive, left negative. So force to the right would be the tension force, to the left would be the friction. So tension minus friction, that's all the left and right forces, so they should balance out to 0. Because I'm going at a constant velocity, I'm in equilibrium. I can do the same sort of thing for the vertical forces, forces up minus forces down, because I'm calling up positive, down negative. So they should add up to 0. The normal force is the only thing going up, and the only force going down is the gravitational. Normal minus gravitational force equals 0. And that's my equations. If I knew a little bit of information, I might be able to solve for the other missing forces. If I knew how big the tension was, I could solve for how big the friction must be. Or if I knew how big the normal force was, I could solve for how big the gravitational force was. I know enough information here, I can sub and solve through. I'm not going to bother with that with this example, but you get the idea. Okay, this one, everything was fine. I'm just looking at one axis at a time, just the left-right forces balancing out, and then just looking at all the up-down forces balancing out, one axis at a time. Let's do a slightly more interesting case. It's going to be just like it. I'm going to pull the book along. All right, it's going to look very similar. Okay, pull it along at a constant velocity, slide, except look, for the side view, you see that I'm not pulling straight to the right. I'm actually pulling up at an angle on the book. All right, and so that's going to make a difference here in our calculation. I'm pulling at an angle upward. Okay, so here's what that side view looks like. There's the book, and I have the string pulling upward. All right, now we're still going to be moving to the right at a constant velocity. All right, but let's make this a little bit more interesting. Let's say that I tell you that tension, I'll say it's fine. Let's just say that I tell you that the tension in the string is, I don't know, maybe we'll say that that's 30 newtons. And let's say that that angle that the string makes with the horizontal, maybe that's 40 degrees. All right. And let's give you one more piece of information. All right. Let's say that the gravitational force, right? Let's say that that is 25 newtons. Okay, so that's how heavy the object is. The gravitational force, the weight, is 25 newtons. And what we want to do is we want to solve for all of the forces acting on the book. So what I'm going to do is I'm going to do my free body diagram. First, technically, I choose my system. Okay, is the first step of next step of solving. You'd say, well, my system is going to be just the book. Okay, now I do my free body diagram for the system. So this box represents just the book. All right. Again, this is that side view, that same view is there. Let's draw in our forces. So you say range forces, there's a gravitational force. No other range forces involved. The force just goes from the center of the object toward the center of the earth. Next, contact forces, what's touching it? Two things, the tabletop, or desktop I'm going to call it, and the string. Let's start with the desktop. Are the desktop and the book being pressed together? And you say, sure, the earth pulls it into the desktop. So the desktop will push back up with a normal force, pushing on that bottom surface of the book. So I start the arrow at the bottom edge of the book. Once you have a normal force, then you ask, are those surfaces trying to slide past each other? In this case, you say, no, is it trying to? It is sliding. It's sliding to the right, so friction goes to the left. That's it for that object. The other thing touching my system is the string. Is the string stressed? Sure, so there's a tension. Tensions always go along the string. So this has got to go along the string. And, which means it's going to make an angle of 40 degrees there with the horizontal. And they always pull, which is why the arrow is going away from the system. It's tugging it. It's not pushing the book down and left. It's pulling it up and right. Okay, that's all the forces. And so my next step would be to use my formula, sigma F, adding up all of the forces. But we're going to do it twice, once for the horizontal direction and once for the vertical direction. We're going to assign our axes like this. Again, we always choose the first axis to go along the motion. This thing is moving left-right, so I'm making an axis that goes left-right. My other axes go at right angles to it, so here's the y-axis. Again, I'm going to choose up and right positive, which is traditional. My horizontal forces should add to 0, and my vertical forces should add to 0. All right, now let's go ahead and write this out. So when I do this, I need to go ahead and talk about my forces left-right. All my forces right should balance my forces left. The problem is, and the new wrinkle here, is this force, it's not just pulling left, right, up, or down. What direction is that arrow going? You see, it's kind of diagonal. It's pulling along more than one direction. It's pulling in more than one axis. It's got a part along the x-axis and a part that's parallel to the y-axis. It's got a part pulling right and a part pulling up. Okay, so not all of the tension is tugging to the right, just part of the force is to the right. So what I need to do is show the pieces of the tension, the components, the piece that's going along the x-axis to the right, and the piece that's going parallel to the y-axis going up. And so to do that, I'm going to draw two arrows, one for the horizontal part and one for the vertical part of the tension. And what I'm going to do is I'm going to draw a chain of arrows that starts where the tension starts and ends where this arrow ends. So that'll look like this. I'll do a dash, 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 dash arrow going to the right. So that's an arrow. It's a dashed arrow that I'm drawing. And then a dashed arrow where that one stops, going up and ending where that original arrow ends. So what I'm saying is that this arrow and this arrow together do the same thing as that diagonal arrow did. These two add up to be equal to that diagonal arrow. They have the same effect. So now the question is, how long are those arrows? How long are the two components that make up this tension T? Now, obviously, if I knew two sides, I could use Pythagorean theorem to find the third. But the only side that I know anything about is this hypotenuse, that's T, that's 30 newtons. How do I find the lengths of these sides? Well, we're going to use trig functions. So just a quick reminder about how trig functions work. A long time ago, someone realized that if I had a triangle, right, a right triangle, not just any old triangle, but a right triangle we're talking about here specifically, that the triangle is going to have three sides. One side is the longest side of the triangle. That's always the side that's across from the 90-degree angle. You say that longest side is called the hypotenuse. These other two sides are called the legs of the right triangle. One of those legs is touching this angle that I know. I'm marking that angle with the Greek letter theta. You say, and the other one is the leg that's not touching the theta, that's opposite it. The one touching it, the one adjacent, we call the adjacent leg. The one that's not the leg that's not touching it is the opposite leg. Well, they realized that there's a certain ratio. If a triangle has this particular angle, there'll be a ratio between how long the side that's touching it, the adjacent side is, that length to the length of its hypotenuse is a certain ratio. And if I make the triangle bigger, but still the same angles, then that ratio is going to be the same. We would say that these triangles, you might remember from geometry class, these triangles are similar triangles. And I can make it even bigger. Again, it's the same ratio. This length that's adjacent to the theta, adjacent to the angle theta, that length compared to the hypotenuse is the same ratio as this length compared to this hypotenuse and this adjacent compared to this hypotenuse. Adjacent hypotenuse is the same ratio for all of them. Well, that's like a useful idea, right? So anytime I have this particular angle, maybe I can remember that it's this particular ratio, or I can make a chart, right? In the old days, you'd look these up on a chart. Same thing with the opposite side. There's a certain ratio between the side that's across here, from that angle theta, that to the hypotenuse, right? It's a certain ratio, and it's the same ratio for the little triangle as for the medium-sized triangle as for the big triangle. Opposite to the theta to the hypotenuse is the same ratio. And so they gave these ratios names, and the logic behind the names and where they came from, not important to know. That's old-timey business. But they started calling this one here, if I'm trying to find the ratio between the adjacent side, the leg that's touching the angle, to the hypotenuse, they called that ratio the cosine of the angle. And the ratio between the opposite side and the hypotenuse, they called the sine of the angle. And that's what these are. And now for different angles, this cosine will have a different value, and there'll be a different ratio of the side lengths. Now, my goal in what I'm trying to do in our physics problem here, our immediate goal here is I want to figure out, hey, how long are these sides of this right triangle? I know the hypotenuse has a length we're calling t. It's 30 newtons long. This is an arrow made out of force. It's 30 newtons of force that way. How many newtons of force is it to the right and how many newtons up? How hard is it pulling in each of those directions? So starting with this side, this is the adjacent. I want to find the adjacent side. So I'm going to rearrange this equation to get adjacent by itself. It's being divided by hypotenuse. So to get by itself, I'm going to multiply both sides by hypotenuse. So the adjacent will be equal to hypotenuse length times the cosine of the angle. Right? So in this case, this side is going to be equal to the hypotenuse, that's tension, times the cosine of the angle. So t cosine 40, that's how long that side is. This side's the opposite side, so I'm going to use the sine function for that. I'll say sine of an angle is equal to the opposite of a hypotenuse. I'm trying to find the opposite length. So rearranging, I'll have to multiply both sides by hypotenuse. So opposite will be equal to hypotenuse length times the sine of the angle. So in this case, the hypotenuse is t, so this side is t times the sine of the 40-degree angle. And that's how long those sides are, using the trig functions. Now that I know how long those sides are, I can now go ahead and use those lengths in my calculations. What I'm going to do is I'm going to be, in my calculation here, I'm going to replace this angle, this arrow, this diagonal tension arrow. Instead of using it, I'm going to say it's the same thing as if I did this and this. This chain of arrows that starts where this starts and ends where it ends, doing this and this is the same as doing that. So for the horizontal forces then, I now have two horizontal arrows. I have this t cosine 40 and this friction force. For calculation purposes, I'm getting rid of this diagonal arrow and I'm just using its components instead, these pieces of it. So in the x, we'll do forces right, because I call that positive, minus forces left, so that'll be t cosine 40 minus friction equals 0. And that's my equation for the horizontal forces. For the vertical forces, now I have how many up and down arrows? Well, I've got 1, 2 going up, and this one going down. I've got 3 arrows in the up and down direction. So that'll be the normal force plus t sine 40, making upward forces, I'm making positive, and then minus gravitational force equals 0. Notice that it's in this step, when I'm plugging into the sigma f equation, the sum of the forces, this is where I use plus or minus to indicate the direction of the force. These variables, n and f and fg and t, those are all positive quantities. It's in this, I don't want my plus or minus sign hiding inside a variable. I want it out here where I can see what's going on. So these are always just, each one is just how big is the arrow, what's the size of it, and they're never negative. I just want these to show the magnitude of the forces. In this step, this is where we put the plus or minus in the sigma f step. That's very important. Okay, so this is how I set up my equations. Now, boom and boom. At this point, typically, once you've subbed into the sigma f equations, pretty much the physics is done, and it's just algebra from here on out. Let me show you how this works in this one. We know the size of two forces, tension, we know T and we know Fg, right? And so I can see that in this equation, since I know the size of the tension, I could solve for the friction force, right? We said there's 4 forces acting in this problem: tension, normal, friction, and gravitational force. And they told us tension was 30 newtons, and they told us the gravitational force was 25 newtons. So there's just 2 left to solve. In this equation, since I know T, I can solve F. And so I'll just rearrange it. T cosine of 40 would equal the friction force. I can sub in my value. 30 cosine 40 is going to be equal to the friction force. Take my calculator, punch in 30 cosine 40 degrees, and that gives me that friction is equal to 22 point, and it says 22.98. I'm going to round that to the nearest tenth. That'll round up to be 23.0 then. 23.0 newtons is my friction force. Okay, let's do the other axis. Okay, notice, by the way, when I substitute in, I don't put the units in the equation. I'm just going to tack the units on at the end. I find it really annoying having unit abbreviations scattered throughout my calculation. It makes it more cluttered and hard to read what's going on. Now let's do the vertical axis. So I'm going to do normal force. Now you say normal, I don't know how big that is, but I do know how big T is, and I know how big the gravitational force is. Those were given to me. So I can solve for N. So that N is going to be, move these to the other side. This says minus FG, so I'm going to have to add FG to both sides to move to the right. And I'm going to need to subtract T sine 40 from both sides. And so now I have the normal force by itself. Substitute in my values. FG is 25 newtons. This tension is 30 sine 40. Go ahead, plug that in my calculator. 25 minus 30 sine 40. And I get 5.716. I'm going to round that off to the nearest tenth, 5.7 newtons. And there is my normal force. And so I found these 2 missing forces. Normal force is 5.7 newtons, and the frictional force is 23 newtons. And that's problem solved. So we took this force and we split it into components because it was pulling along more than one direction. It was pulling both right and up, along the x-axis and along the y-axis, along the motion and perpendicular to the motion. And so we replaced T with its 2 components, and then used those in our equations. And that's it. That's the idea, is that when I've got forces at angles, I want to split them up into pieces going along each of the axes that we're interested in. And so I can see how the forces are affecting the motion and the forces that are sideways to the motion. And that's the main idea. Do you want to see one more problem like this, or is this good? Well, let's go ahead and show you one more. Nah, this is fine. I just want to point out just one last thing about this, and that is, hey, that tension force that we split into pieces, it doesn't, first of all, it doesn't have to be tension. Any force might be at a weird angle and be split into pieces for us. Okay, you'll see that as we do more problems. I might have someone pushing on a block and pushing at an angle on it, for example. The second thing I want to point out is, in this problem, does the normal force balance out the gravitational force? Are those 2 equal to each other? And the answer is, well, no. The gravitational was 25, the normal is just 5.7. Why? Because the string is tugging up on the book. It's making it so it's not pressing into the tabletop quite so hard. This is balancing out part of its weight. And so the tabletop doesn't push back as hard. It's not being pressed as hard into it. These 2 together are balancing out the gravitational. Okay. That, I think, is what I wanted to show.